and thank you for joining me today. I'm Chen from Nanjing University, China. I'm so excited to be here to share with you the results of my recent research. My topic today is the evolution of social-ecological system interactions and their impact on the environment of major Chinese cities. The content may be different from the previously submitted abstract, but I think it more closely matches our theme. Yeah. Here is overview. There are three parts. To begin with, I would like to introduce some background information of this study. First, why study heat? A city is a complex social and ecological system. Changes in urban landscape and climate cause changes in urban thermal environment. In the context of global warming and urbanization, urban heat island and heat wave have caused a widespread concern. And overheating in cities results in a number of negative impacts, including increases in heat-related mortality and heat inequality. So heat mitigation is crucial to achieving sustainable urban development. So next, we need to understand what factors affect urban heat. The type and structure of urban landscape directly affects urban thermal environment. Many studies have shown that multiple social and ecological factors influence the thermal environment, but mainly single-factor analysis. Few studies explain the impact of interactions between social and ecological factors on the environment, which limits the development of a comprehensive strategy for heat mitigation. Yeah, in view of this background information, I would like to introduce the objective of this study. First, to learn about the evolutionary characteristics of the environment is an important starting point for heat mitigation. As we all know, China has experienced rapid urbanization over the past few decades, with an increase in urban population and deterioration of the environment. But in recent years, many Chinese cities have also adopted ecological conservation measures. Therefore, we propose a hypothesis. Does the relationship between the evolution of urban thermal environment and urban development conforms conform to the classical environmental coordinates curve, showing an inverted U curve? That's the first objective. Apart from that, recently, social ecological system concepts have the potential in addressing social and environmental challenges. So in this study, we propose a framework for regulating the urban thermal environment with a social ecological system. Since SES is a complex system, coupled the social and ecological subsystems, the foundation of the SES is factors, and the interaction between social and ecological factors forms a pathway that connects the two subsystems. And this structure evolves during rapid urbanization and affects the thermal environment. That's why the second objective is to explore the impact of social ecological system interactions on the thermal environment. The next part is data and methods. This study focuses on China. Following the strategy of ecological civilization construction, China's urban development shifts from urban expansion to the balance between economic development and ecological protection. We select 136 urban areas as samples in this study. In these cities, the urban population is more than 1 million and the area is over 100 square kilometers. Meanwhile, we have collected multi-source remote sensing datasets, and urban area boundary and land surface temperature are used to calculate the thermal environment, and other data are used to quantify social and ecological factors. In this study, thermal environment is quantified as the difference in land surface temperature between urban area and the reference area in the same year. Firstly, we calculated the delta T of each urban area year by year from 2000 to 2021. And then, ordinary least squares linear regression was used to analyze the general trend of delta T. Finally, piecewise linear regression is employed to detect the existence of inflection points. As for social-ecological system, we have explored the impact of various factors, pathways, and the system on the thermal environment in turn. Firstly, factor detect model in geodetector was used to analyze the role of single social or ecological factor. Next, interaction detector model was used to explore the combined role of social and ecological factor. Lastly, we have constructed a social-ecological data index oriented to the thermal environment based on the concepts of resilience and pressure. The index reflects the structure and the developmental state of SES. The following part is results and the discussion. For spatial temporal trends in thermal environment, there are 42 urban areas with inflection points, which reveals the nonlinearity in the temporal trends of thermal environment intensity. And then 136 urban areas are classified into five evolutionary patterns, including continuous increase, as shown in graph C, steady to fast increase, showing graph D and E, fast increase to slow increase in graph F, increase to decrease in graph G, and irregular changes. Based on the observed patterns of change over time, thermal environment trends are classified into fast increase, slow increase, and decrease phases. Delta T slope greater than zero point 0.1 in fast increase phase, delta T slope greater than 0 less than zero point 0.1 in slow phase, and delta T slope is less than 0 in decrease phase. The next results are the impact of SES interactions on the thermal environment. Single factor analysis shows that economic development is a key social factor, while vegetation quality is the dominant ecological factor. Interaction factor analysis shows that the interaction of social and ecological factors has a higher impact on the environment than a single factor. This result clearly indicates that urban heat mitigation strategies need to evolve from a single factor approach to multiple factor SES interactions. From a systematic perspective, system index indicates a significant difference across the thermal environment phases. The decrease phase has the highest index value. We further explore the relationship between SESI and delta T trends through piecewise linear regression. Based on that, the results show that when the SESI value is higher than the threshold of 0.414, the environment is more rapid mitigated. Spatial analysis reveals the recent SESI values have significant difference between urban areas, with 31 urban areas having values greater than the threshold. By now, we have revealed the priority area for future heat mitigation. So, how should this city develop? For example, Beijing, it has a good set of SES with social and ecological factors showing an increasing trend. That means win-win solutions for urban society and ecology contribute to heat mitigation and promote sustainable urban development. Okay, this study reveals the evolutionary characteristics of urban thermal environment and explored the impact of social-ecological system interactions on urban thermal environment. After summarizing, we found that the relationship between urban development and evolving thermal environment conforms to the environmental coolness curves. When the city enters the advanced development phase, ecological factors limit or supervise the thermal environment at this phase, but this is synergy with social factors. Now, some urban areas have already shown a decreasing trend in thermal environment, which is closely related to a series of ecological measures in China. Previous studies have shown that from 2000 to 2017, China accounted for 25% of global net increase in leaf area. Focusing on urban scale, more than 60% of urban areas in China's major cities have a greener trend over 2010 to 2019. In summary, in this study, we suggest a win-win pattern for urban, social, and ecological co-development to achieving heat mitigation. Thank you.
Questions? We have time for one or two questions. Do you have any question? All right. Thank you.